Hi, everyone. In this video, we will begin our discussion of second-order partial derivatives. We've spent the past several videos discussing first-order partial derivatives. For example, taking the derivative with respect to a particular variable of a multivariable function, or taking directional derivatives. In this video, we want to understand what a second-order partial derivative is, begin to look at some of the properties of second-order partial derivatives. And in future videos, we will learn more about what second-order partial derivatives can tell us about the behavior of a multivariable function. So to begin, we first want to define what a second-order partial derivative is. So if we think back to calculus or the first course in analysis, we would have defined a second derivative as the derivative of the first derivative. Now, in that case, we only had a single variable, so there was only one second derivative to discuss. However, now that we're dealing with multivariable functions, we have many first derivatives, right? We have sort of a derivative with respect to the first variable, with respect to the second variable, all the way up to, say, the derivative with respect to an nth variable. And then if we want to take a derivative of one of those derivatives, we still have n choices, right? So for a function of n variables, there are n squared number of functions that could sort of lay claim to being something like a second derivative. So we want to define these second-order partial derivatives in a similar way, but also, again, recognizing that there will be many types of these. So imagine f has a partial derivative with respect to the kth variable. So we would write that as d sub k of f. We might also write that as partial f partial x sub k, right? That's assuming you sort of named your variables x1, x2, x3, all the way up to xn. Then we might express the derivative with respect to the kth variable in this way. Now, this partial derivative will be a function of n variables, right? So this partial derivative with respect to the kth variable is itself a function of the n variables x1, x2, all the way up to xn. So if that function itself has a partial derivative with respect to, say, one of the other variables, xj, then we can take the derivative with respect to the jth variable of the derivative with respect to the kth variable of f, and we call that partial derivative d sub jk. So this is the notation we'll commonly be using, d sub jk. And really what that means is take the derivative with respect to the jth variable of the function, which is the derivative with respect to the kth variable of f. Okay, so again, what we're doing is we're just composing this differentiation operation in exactly the same way we did for functions of a single variable. It's just that now we have a lot of different sort of second derivative type objects. So we call each of these a second order partial derivative. So if we're in the case, for example, we're just a function from R2 into R, so we just have two variables, say x and y, then there are just four second-order partial derivatives. So if you're in R2, there are two squared second-order partial derivatives. So they're d11, d11 of f, d12 of f, d21 of f, and d22 of f. Again, we could use other notation, so we might just also express this, let's say, as d squared f over dx squared. So again, this looks similar to just like a second derivative with respect to x. These are just partial derivatives here. But once we get into these mixed partial derivatives, so for example, d12, that would be d squared f d, so we're d12, so dx, or partial x, partial y, okay? And again, we sort of think about what we're doing to f. First, we're taking a derivative with respect to y, a partial derivative with respect to y, and then we're taking that partial derivative of f with respect to y and taking a partial derivative of that with respect to x. Okay. Similarly, we could express this as partial derivative with respect to dy dx, and then our partial y, partial x, And then this would just be d squared f dy squared. Okay. So again, same notation. They mean exactly the same things. Now, in this video, we want to first spend a little bit of time just sort of making sense of these second order partial derivatives. And one way we're going to do that is we're going to do that through just working through a couple of examples. One of those examples I will actually expand further in a subsequent sort of additional video where we'll actually visualize that example and help understand conceptually what these second order partial derivatives are trying to capture. So I'll actually upload a Desmos 3D visualization that you can play around with, and also a video just walking you through how to use that visualization and what it is showing you. But again, it will be based around one of the examples, actually the first example that we're getting ready to look at. So we want to just understand, what are some properties that these things have through just working through some examples. All right, so let's begin with just the function f of xy is equal to sine of x times y. Okay. Now, again, just sort of quickly to run through, right? We have 4 second order partials here, right? So I have d11 f of xy, d12 f of xy, d21 f of xy, and d22 f of xy. Okay. Now, I'd like to see if I can just quickly sort of calculate each of these. But notice, before I can get any second partials, I first have to understand the first partials. So I need d1 f of xy, and I need d2 f of xy. Okay. So d1, that's just derivative with respect to the first variable. I could also write partial f, partial y. Okay. And one of the things we saw previously is if I'm just taking partial derivatives, it's totally valid to just consider y, say here to be a constant, x to be the variable, and just take the derivative in that way. So here, if I let y be a constant, I'll get y cosine of xy. For d2f of xy, right, that's derivative with respect to y. Now I pretend x is a constant, so I'm just going to get x cosine of x times y. All right. Now, d11 and d22, right, in a lot of ways are the easiest things to calculate because sort of don't have to worry about order, right? d11 is just take another first derivative, another partial derivative of d1, but just with respect to x again, okay? So here, I'm just going to take another partial derivative with respect to x. I'm pretending y is constant, and I get this, okay? Similarly, if I want d22 of f, right? Well, that would just be take another partial derivative of d2 with respect to y, d2 of f. So just take another derivative of this with respect to y. That's going to give me minus x squared. Oops, sorry, that should be sine of xy. Okay, great, no problem. Everything's working out fine so far. Now, for these two interior ones, we need to be a little careful. So the question is, like, I know that for each of these, I'm going to take a derivative with respect to the other variable. So here first I took a derivative with respect to x. Now I'm going to take one with respect to y, but which one of these is that? So I already have d1 of f. Now if I take a derivative with respect to the second variable, right, I'll get that. So that would be d2, d1, or d21. So d21 is take the derivative of d1 with respect to the second variable. So now I need to take a derivative of this with respect to y. Well, if I'm going to do that, I need to use a product rule. So again, I'm going to imagine y is a variable, x is a constant. So using the product rule, I'll get cosine of xy. And then I'll leave the y alone, take a derivative, and then I'll get a minus xy cosine, or sorry, sine of xy. All right. Now, to get d1, 2, I'm going to take a derivative with respect to the first variable of the derivative with respect to the second variable of f. So now I'm going to take a partial derivative of this expression with respect to the x variable. Okay. So I come over here again, I'm going to need to use a product rule. So I'm going to get a cosine of xy minus, now let's see, leave the x, or so it would be plus, but I'm going to take a derivative of this cosine and get a negative sign. So I'm going to get a y that comes out here. So I get a minus yx sine of xy. All right, so this is just like standard Calc 3, calculate the mixed partial derivatives. Okay. Now, one of the things you may quickly notice is that while I was very sort of particular about making sure I took these derivatives in the right order, at the end of the day, these two expressions are equal for every value of x and y, right? And so you might reasonably start to wonder, so, I mean, I've written sort of equals question mark here. For sure, these two expressions are equal for every x and y, for every real x and y. So the question is that true in general? Or maybe this was just a really nice function, right? And like one of the things that might concern you about this function is that you'll actually notice f of xy is equal to f of yx, right? If I just swap the variables around, right, like I still get the same expression. So maybe there's something going on there, right? Like maybe this is just sort of a special case. It actually turns out it's not this property that makes this work. So you could take something like, you could try, maybe this will be like example 1.5, right? So take f of xy to be x squared plus y. This function does not have this property, right? This function, if I swap x and y, I get a different function. So if I do this and I take, well, so let's just quickly, so d1 f of xy would just be 2x, and d2f of xy would just be 1. Okay, so d2 1 f of xy. So let's take a derivative of this with respect to y, that would be 0. And d1 2 f of xy would be take a derivative of this with respect to the first variable, but you'd also get 0. So you still get that these are both equal, even though this function doesn't have this symmetry between the variables. So certainly, right, through a number of examples, right, it seems like maybe something's going on here, right? Maybe this is always the case. So you might start to wonder if this is always the case. Now, I think I mentioned earlier there's 2 examples. So you might be guessing that in the next one, we'll see that this is not true. I think you should be a little skeptical of this always being true, though, because we've already seen that with multivariable functions, you know, things like differentiability and even continuity, there's just more room for things to go wrong. So having some really nice property it just seems unlikely. Now, again, that doesn't mean it's not true. That doesn't mean that there aren't nice theorems in multivariable analysis. It just means typically I'm going to be a little more skeptical of a claim like that. So let's then look at another example. So let's consider this piecewise defined function. So this function is x times y times x squared minus y squared over x squared plus y squared, as long as x and y are not both simultaneously 0. And if x and y are both simultaneously 0, then the function will return the value 0. So let's make it our goal then to try and calculate the mixed partial derivatives. Okay. So in order to understand the mixed partial derivatives, so let's say I want D12 F, and let's just focus on 0, 0, right? As you might guess, something a little strange is going on here. So let's try to calculate these two mixed partial derivatives at 0, 0. Now I'm choosing to take a particular point because the first thing I want to do is I can't just start differentiating things here because this is a piecewise defined expression. And if I want to know the value of these mixed partials at 0, 0, I've sort of got to pause for a second and figure out what that even means. I can't just start taking derivatives. So this means what? Derivative with respect to the first variable of the derivative with respect to the second variable of f, and then we're going to evaluate that at 0, 0. So if this were just some function, and I was trying to find the partial derivative with respect to the first variable, we would just say, well, that's the limit as h goes to 0 of this function that I'm taking the derivative of, evaluated at 0, 0 plus h times, now I'm doing a partial derivative here, and so I'm going to just do this in the direction of the standard basis vector in the first variable direction. Minus this function evaluated at 0, 0, all over h. So if I just write out what this is here, this is the limit as h goes to 0 of d2 f of h0 minus d2 f of 0, 0 all over h. Now, if I write something similar out here, I'm going to skip sort of the intermediate step. You should be able to repeat this. The only thing that's going to change is I'm going to have ones here and here. And now here, this will be the vector E2. So it'll be 0, 1. So what I'll end up with is D1F of 0H minus D1F of 0, 0 all over H. So what I sort of understand from all of this is if I want to make sense of what these mixed partials ought to be, then there are really four quantities I need to be able to make sense of. So I need to be able to make sense of my first partials, right? I really should have put that one. First partials at 0, 0. So I'm going to need to understand D1 f of 0, 0 and D2 f of 0, 0. Okay. And then I will also need these. Grab a different color here. These mixed partials. Notice that these are at a point that is not 0, 0. Okay, so I need the mixed part, the first, sorry, not the mixed partials. I need the first partials at 0, 0, and I also need the first partials at points that are not 0, 0. So I'm going to need D1 f of 0h, and I'm going to need D2 f of h0. Okay. Now, actually, I'm going to find these by first just finding D1 f of xy for a point xy that's not 0, 0. And similarly here, I'll first just find D2 f of xy. Okay, once I have that, I'll be able to get this. All right, so let's erase a bit here. We will have to come back to these expressions, but let's give ourselves a bit of room to see if we can figure out what these four things are. Then we'll come back to actually calculate the mixed partials. All right. So it actually turns out that for xy not 0, 0, for x and y, not both simultaneously 0. Wasn't careful there. I ran into the displayed text. So there's a little room here. Okay. So if x and y aren't both 0, okay, well, we can just differentiate this expression, right? We can just take partial derivatives, right? We don't need to do anything really fancy here. So I'm actually just going to go ahead and write out what happens. So you want the derivative with respect to the first variable of f at xy. So you just come here to this expression. You pretend y is a constant, and you take a derivative with respect to x. Now, what do you have to do? Well, you've got a product here. You have a expression here that involves x and an expression here. So you got to do a product rule. And then to take the derivative of this piece, you have to do a quotient rule. So I'm just going to sort of give you what you should get out. You should be able to calculate this and simplify it. But let me just sort of cut to the chase here. So you get for this y times x to the fourth plus 4x squared y squared minus y to the fourth all over x squared plus y squared squared. Okay, that's that derivative. It actually turns out that to find d2 f of xy, now you could just come here and pretend x is a constant, take a derivative with respect to y. That'll give you the right answer. But you can actually be a little bit clever here if you note that f of xy is equal to negative f of yx. Okay, so notice that if you substitute y in everywhere you see x and x in everywhere you see y, these xy just becomes yx, so that's the same thing. X squared plus y squared just becomes y squared plus x squared, which is the same thing. And in the numerator, x squared minus y squared becomes y squared minus x squared, which is different, but it just negates things. Okay, so because you have this, if you wanted to take a derivative with respect to y, the y variable, right? So that would be here taking a derivative, with respect to the second variable. Well, here to differentiate with respect to y, it's the first variable that depends on y. So you'd get negative derivative with respect to the first variable of f of y x. Okay. So what is that telling me? It's telling me that to take this derivative, I could also just swap the inputs x and y and negate the thing that I had up here. So if I just negate this whole thing, and now everywhere I see y, I'm going to put an x, and everywhere I see x, I'm going to put a y. So I'll get x, y to the fourth plus 4. I also get an x squared, y squared here, minus x to the fourth all over. This will still just be x squared plus y squared squared. So that's a little sort of cheat, to quickly get that derivative. All right, so great. We have both of these, but notice that, right, my goal here really was to be able to calculate this, right, these. So I've now gotten the partial derivatives at an arbitrary point xy. Now I'm going to substitute in, let's see. So I'm now going to take this to calculate d1 f of 0h. And well, let's see what happens. So if I substitute in, let's see, x is equal to 0, y is equal to h. Okay, so x is equal to 0, so this term and this term both become 0. I just get an h times a minus h to the fourth. I get a minus h to the fifth in the numerator. In the denominator, I'm going to get a 0 squared plus h squared. So it's just a h squared squared. That's a h to the fourth. And again, I'm assuming here h is not 0. So this just gives me an h. Okay. Oh, sorry, a minus h. Here, d2 f of h0. I go through a similar process, okay? But now let's see, I have a minus here, so I'm going to get a minus h times everything in here. This will be 0, this will be 0. This will be a minus h to the fourth. So I've got a minus h times a minus h to the fourth. That's going to give me a positive h to the fifth. In the denominator, I'm going to get h squared plus 0 squared. That's h squared squared, which is h to the fourth. So here I'm just going to get h. All right, so this actually worked out really well. This is minus h. This is h. Okay. Now, the d1 f of 0, 0 and d2 f of 0, 0, I can't just sort of differentiate a formula here because now I'm at this particular point where this has a this pointwise has its own definition. Okay. So let's actually just see what we can say there. Okay, we'll have to go back to the limit definition. So if I want to calculate d1 f of 0, 0, okay, well, what is that? That's the limit as h goes to 0. I'm going to do a similar thing I did in expressing it before. So this is going to be f of 0, 0 plus h times 1, 0. Okay, minus f of 0, 0 all over h. So again, notice what we're really doing is we're fixing y at 0, and we're incrementing the h or the x variable. Right. All right. So, well, let's see. What is this? This is just the limit as h goes to 0. F of h time or h 0. Well, if y is 0, this whole expression is 0. Right. So for h 0, I'm assuming h is not 0, so they're not both simultaneously 0. I use this expression, but y is 0, which makes this whole expression 0. So this is 0 minus f of 0, 0, which is 0, all over h. This is just the limit as h goes to 0 of 0 over h. It's just 0. Okay. A nearly identical argument, d2f of 0, 0, is going to be the limit as h goes to 0 of f of 0h minus f of 0, 0 over h. And again, this will be a limit as h goes to 0 of 0 minus 0 over h, which will be 0. So as it turns out, both of these are 0. All right. So now these were the sort of components we needed in order to understand the mixed partial. So let's go back then to those expressions for the mixed partials. So let's start with d1, 2, f of 0, 0. Okay. So we have expressed that as a limit as h goes to 0 of d2 f of h 0 minus d2 f of 0, 0 all over h. Well, now we know what these pieces are. This is the limit as h goes to 0. d2 f of h 0, that's just h, minus d2 f of 0, 0, that's just 0 over h. Well, this is just 1. What about d21 f of 0, 0? That's a limit as h goes to 0 of d1 f of 0h minus d1 f of 0, 0 all over h. And well, we know what all those pieces again are. d1 f of 0h, that's minus h, minus d1 f of 0, 0, that's just 0, all over h. This is just negative 1. And so we see here that the mixed partials are not, in fact, equal to one another. Okay. So we now know that certainly it does not have to be the case that the mixed partials are equal to each other, but at least for like some of those other nice examples we were looking at, sort of seemed like it was the case. And so, well, as we often do in analysis, a reasonable next question to ask would be, what are some sufficient conditions in order to ensure that the mixed partials are equal to each other? Okay. Now, there could be a question of, why, well, why should I care, right? Like, I mean, yeah, maybe it's just convenient computationally if sometimes I can go, oh, these mixed partial derivatives have to be equal to each other. But, what does that actually get me? Well, to sort of preview forward a little bit, one of the things we're going to want to understand really is, just as we did with sort of first derivatives, we saw that just understanding all the partial derivatives really doesn't give you a notion of differentiability, right? And in the same way, we want something that sort of encapsulates a second derivative, but we've already seen there are like at least 4 types of second derivative object, right? And so a very reasonable question to ask is like, which one is the right one, or how do I use all of them together? And so one possible one thing we'll look at is you can actually construct a matrix of the second partial derivatives. And we'll actually give a name to this matrix. It'll be called the Hessian matrix. And one of the things you can note is that if you are actually in the case where the mixed partials are equal, this matrix is symmetric, right? Because it's its own transpose. Okay. Now, if you haven't taken linear algebra yet, you may or may not have seen some stuff in an undergraduate linear algebra course about symmetric matrices. You may have seen more if you've already taken the graduate linear course. But it actually just turns out that we have symmetric matrices are a little nicer than other kinds of matrices. We can say some additional things about symmetric matrices. And so it's actually nice from a theoretical point of view to know if those mixed partials are going to be equal, because it makes sure that second derivative matrix, that Hessian matrix, is symmetric, which has some added benefits. Again, we'll discuss more about that a little later on. But just to sort of preview forward, like, I think it's a reasonable question to ask, why do we care if the mixed partials are equal? And that gives you at least one possible explanation. So again, we want to understand when this is going to be the case. Now, we're going to conclude this video by actually looking just at the theorems that tell us sort of some sufficient conditions for equality of those mixed partials. We will actually prove one of these theorems in the next video. Okay, so I just want to give you a sense of what the theorem is saying here. There's a sort of relationship between the two theorems I'm going to show you, and we'll talk about those two. So this theorem, sometimes called just equality of mixed partials, Clairaut's theorem, Schwarz's theorem, it essentially just says the following, and I'm going to just state these. You can actually say these, you can state these theorems for functions of more than 2 variables, where you're just looking at particular combinations of second mixed partials. But I'm just going to state them for functions from R2 into R. So let F be a scalar field defined on an open set S in R2. And suppose that the partial derivatives d1 of f, d2 of f, and d21 of f exist on this set S. Okay, so my first assumption is simply that both of the first partials exist and one of the mixed partials exists on this set S. Additionally, I want to assume that that same mixed partial, it doesn't just exist on S, it's actually continuous at a point A in S. So if you know that both the first partials exist, one of the mixed partials exists, and that same mixed partial is continuous at some point A, then the other mixed partial must also exist, and the mixed partials must be equal to one another. Okay. Now, this is sort of what I would call the stronger version of Clairaut's theorem. I mean, this is typically when somebody says Clairaut's theorem, this is what they're thinking of. What I want to point out is that there are actually two pieces that you conclude here, right? It's not just that you get equality of mixed partials, although that's often sort of what you're after. You also get the existence of this other mixed partial, which obviously you couldn't have equality of the mixed partials if the other mixed partial didn't exist. It actually turns out in proving this version, you actually spend quite a long time just trying to argue that this other mixed partial has to exist. Now, that's a valuable thing, but unfortunately what it does is if you prove this version of the theorem, you spend a lot of time proving that existence piece, and you get to the equality piece, but it sort of actually feels like the easier part, and it's sort of secondary, okay? So what I actually want to do when we go to prove this theorem is I want to prove a slightly weaker version of this theorem. Now, when I say a weaker theorem, what that typically means is I'm going to make stronger assumptions, right? Making stronger assumptions means that my theorem applies in fewer cases, so it's weaker, right? So what I'm essentially going to do is I'm sort of going to just move this business about this other mixed partial existing. I'm actually going to move it to an assumption, and I'm actually going to even assume a little bit more, which is I'm going to assume that this mixed partial is also continuous at A. So the weaker version that we'll actually prove is let F be a scalar field defined on an open set S in R2. Now we're going to go ahead and assume that both of the partial derivatives, the first partials exist, both of the mixed partials exist, and that both of the mixed partials are continuous at A. Then we will prove that the mixed partials have to be equal to one another. Now, you'll notice I've actually included on both versions of this theorem, theorem numbers. They actually correspond to the theorem numbers in the book. So we will prove theorem 812, which is, again, the weaker version. What the book does is it proves this weaker version, and then it goes on to additionally prove the stronger version, the sort of full Clairaut's theorem. So we will prove in the next video theorem 812. We'll talk a little bit about how you would extend this to theorem 813, but you can find the full proof in the book. Okay. That will conclude this video. Again, in the next video, we will work on proving these theorems and also beginning to discuss the Hessian matrix and what we can learn from the Hessian matrix. I would encourage you, after concluding this video, to go watch the supplementary video that I'm posting along with the Desmos 3D visualization to just help build or help refresh some of that conceptual understanding of what these mixed partial derivatives are telling you about a function.